Hi and welcome for another episode of Quadratic Sieve running on Java. My name is Ilya Gazman. Let's hack. In episode 3, we're going to talk about a stress tool. So far we spoke about tree optimization for the Fermat factorization method. We look at small modes at square n power 2, and then we use a congress of squares to increase the values that we are examining to not only look at the difference of squares, but also their multiplications. And finally, we examine the possibility of adding a small integer k, multiply n by a small integer k before squaring it. Okay, so we created three programs, episode 1, 2, and 2.1. Now let's build a stress tool to compare the performance of those algorithms. And also let's add a trivial division as another comparison. Let's go. So let's start by adding a stress tool. We're going to call it stress. Stress. We'll give it a bit length. Bit length. And also the time in milliseconds that we expect the stress tool to run. During the stress tool, we want to suppress the logs. So let's say if logs available, if logs are not available, then down. Okay, so it's false by default. Uh, logs true by default. So we block the logs and let's okay. And now let's run the stress. So during the stress, we are just going to call for the start method. Let's record the starting time. Start time. Oh, we already have a start time, which is a system nanoseconds. Cool. Using it for logging. Okay, so let's reuse it. And while system runtime minus start time is smaller than the time in milliseconds multiplied by nanosecond conversion. During this time, we're just going to run the solve with the bit lengths. So we're going to run the start with bit lengths. Our logs are disabled, and when it's done, let's count how many we made. Okay, and now let's see how much time it took us. to execute this many counts. Let's log it. So I want to bypass that. Just so I'll go now true and log count and speed. So speed is count divided by this difference. Give us the time in nanoseconds. We want it in milliseconds or even seconds. So let's multiply that by second multiplier, and we want it to be double to see the results. Okay, so we have the speed, call it speed, and we have the count. So this is our stress tool. Oh, and we need to make our random, since it's pseudo-random, to not be initialized in the start. Put it here. Okay, so now we can call to stress to measure performance. Let's try it. So let's start with episode 1. And instead of start, let's do stress of 30 bit lengths with 1 second. It takes its time. Oh yeah, we run it in here 10 times. So let's remove that. We don't want to run it for 10 times. Just 1 time is enough. So replace it just with R2. And once you log it, then return. Let's try again. Let me fix that. Okay, so the problem is that it doesn't stop for some numbers because they are not exactly n bit lengths divided by 2 plus 1 of the size. So let's change it to accept more options and try it now. Okay, so it's 53 times, almost 54 times a second. Change it to 5, 3. And stack. Oh, 46. Okay, so let's keep it on 5. 47. All right, so the speed of a Fermat algorithm unoptimized, it's 47 times a second. Let's do the same thing for other algorithms and see what's going on. So for the optimization where the numbers are closer to the root, and we're using converse of squares. Let's see. All right, so it's much faster. It's 219 times a second. Right, and now for our latest optimization. So that. Right, it's about 3 times faster. And just to take things in perspective, let's also add a new algorithm. Let's call it, in fact, for trivial division. Trivial division. Okay. S 30 for 1 second. And the algorithm is going to be, um, let's start with n square and keep going up until we find a solution. So square at begins with value of I, and let's see if n n for that is equals to 0. If it's indeed the case, then log got it, and the solution is that square and I. Okay, let's call it 3. And then break factory and put trial run first. Yeah, it works. Oh, super fast, by the way. Let's do a stress tool for it. For 1 second, let's go. Okay, so 294. It's the trial division is actually better than the basic Fermat algorithm. And also, what was the value here? The congress of squares. Yeah, seems that it's run faster than that. Remember higher value earlier. Yeah. So I guess my PC is also important. Let me tell you what is my PC architecture. So I'm running a 64-bit Windows 10, and I got 60 gigabytes RAM, 2.5 gigahertz. Yeah, it's kind of standard today, right? So those are the performances. Now we know that this optimization really works for small value of case. It can run much faster. So the results of this stress test are pretty random, I must say. The value before was higher. Um, Interesting. Oh, one thing that we are missing is probably a warm up. So it's not this Tesla is not a very efficient, because there are other stress tools that you need to consider when testing Java implementation. But it can give you like a super rough estimate about what's going on. Um, let's just add a quick warm up, because this one is important. And let's give it a form of 10 iterations. Let's do it again, the stress still. Yeah, no idea. Oh, because it includes the starting time from the beginning. We need to set the starting time from when the stress is starting. So let's use a different variable for it. And so we just use it locally. So we can do it like that. Now we have a local start time. And we wanted start after the first few iterations. Okay, for episode 1, 21. What's going on? Okay, no idea. Probably something running in my background that eating up CPUs. This is why we see such a difference. But nevertheless, it's always faster the optimization of small value of k. All right. We'll continue next time with a more strong optimizations. Please post your questions in the Facebook groups and or comment below, and check out the source code in GitHub.